And so the main learning objectives today are to understand and use SI units, the Système International, especially derived units, and understand the difference between precision and accuracy and how that relates to significant digits. We want to be able to report results with the proper number of significant digits and properly convert between different measurement units. These are two very important topics that people get hung up on a lot. So we're actually going to spend time on that and some practicing. There's going to be several different videos. This is just the first one, and where I'll go over SI units, and there'll be separate chunked videos that look at significant digits and looking at conversion between units. Okay, SI units. So we can sort of divide SI units into fundamental units and derived units. Fundamental units are things that you need to have a single amount for. You can't treat it in terms of the other quantities. And it turns out that there are only seven fundamental SI units of measurement. Any other unit you see can be derived from these. Those are the units of mass, which are the fundamental unit is the kilogram. Seems kind of silly that it's the kilogram instead of the gram because you got the prefix there, but that's what it is. And its abbreviation is kg. Length, the fundamental unit is the meter, abbreviation small m. Temperature, name of the unit is Kelvin. The SI unit is Kelvin. And then amount of substance is a mole. We'll talk a lot more about that in terms of stoichiometry, but you need to have some way to define the amount of a substance. Time, unit is a second. These are all things that are pretty common. Things you'll see a little less frequently, electric current, we'll get into that in the very end of class. The unit is the ampere, abbreviation is capital A, and luminous intensity, the amount of light, candela, abbreviation CD. I do not think we will ever use that in this class. But those are the seven fundamental units. What almost all the other units are going to be derived units. So what are the common derived units we'll deal with? We'll deal with a lot more, but these are the most common ones that you see a lot. So area. That's something that comes up quite a bit. An area is defined as meters squared. As you know, it's going to be the product of two lengths. The derived unit, we just don't use another name for it. We just call it meters squared. Volume, that's pretty easy. If you've got area, then you're going to have volume as well. The unit there, because a volume is the cube of a distance, the fundamental unit of volume is meters cubed. Now, there are certainly derived units we use. For example, a liter is 10 to the minus third meters cubed. Because a meters cubed that's a lot. A cubic meter, you don't really go to the store and buy a cubic meter of water. That's just a little much. A liter, 1,000th of a cubic meter, is a nice amount you can carry around with you. Density is going to be kilograms per meters cubed. Frequently, we'll use grams per centimeter cubed. Because those just seem like a little more natural units if you're dealing with small amounts of things. We usually, again, a centimeter cubed is a reasonable amount of volume to be dealing with. A meter cubed, again, is a large volume. So, and also kilograms per meter cubed, if you look at common substances in kilograms per meter cubed, the numbers are quite small. With the grams per centimeter cubed, it turns out those are numbers that are nice and near one. For example, water, we know, is 1 gram per centimeter cubed. That's actually sort of the definition of the gram. So generally, things like liquids and solids have densities that are somewhere between 0.5 grams per centimeter cubed up to maybe 15 grams per centimeter cubed for a really heavy metal. So speed is going to be in meters per second. You'll either see it written as a ratio like this, meters per second, or frequently meters times seconds to the minus 1. And there's really an implied multiplication here. Sometimes you'll see a dot between them, sometimes you won't. Sometimes multiplication will just be implied by juxtaposition. And there's no real derived units there, we just say meters per second. Of course, you could have a number of other derived units. You could imagine something being written in centimeters per second. That's another derived unit. Or you of course can define all sorts of other speeds in non-SI units. Furlongs per fortnight, perfectly reasonable. Measurement of speed units, I don't know why you use it, but it's perfectly reasonable to express any speed in terms of furlongs per fortnight. Generally, we won't be doing that. Acceleration is another important derived unit. Acceleration is going to be meters per second squared. How much velocity you're gaining per second, much velocity you're gaining per second. This most commonly comes up in gravitation. The gravitational constant had units of acceleration, how much an object is going to start accelerating towards the center of the Earth, about 3.81 meters per second squared. Again, we don't really have a name for that unit. It's just, we just say meters per second squared. There's no special name for that. Okay, so those are some pretty common derived units, and those are pretty straightforward. You've dealt with these a lot. Just the things to watch out for are remembering, for example, if you see something like this, that is going to be the same thing as meters per second. Just meters times second to the -1, same thing. Sometimes it's just easier to have everything on one line instead of having to deal with multiple fractions. Okay, so those are the simpler derived units, but things can get a little bit more complicated. For example, force. Force is a very important unit we deal with a lot when you're looking at conservation of energy in physics. You've seen this a lot, but maybe your physics, we know you're good at chemistry if you're in this class, but you might not have as much physics. So force is defined by mass times acceleration. F equals ma. That's really all it is. F equals ma. And the derived unit here is the Newton. So as you could guess, the units of the Newton are kilograms, that's the mass, times acceleration, meters per second, inverse second squared. So we give it the name Newton, but really you could think of it in terms of the fundamental units, kilograms times mass over second squared. We name it the Newton because, you know, Isaac Newton, you know, he came up with F equals ma. So that's something we'll see a lot. Right, next is pressure, which is force per unit area. And therefore its units, which we call, give the name pascals, are newtons over meter squared. Newtons over meter squared is kind of a big mouthful, so we use pascals instead. There are other units of pressure. Atmosphere is a very common unit of pressure. Millimeters of mercury actually is a unit of pressure as well. And, but the SI unit is pascals. Now, we usually define it as newtons per meter squared, but you can write it in fundamental units as well. Let me switch to another view here. All right. Okay, so if it's force per area, we know that a Newton is, just from right up above, a Newton is a kilogram meter per second squared. And then that's going to be divided by meters squared or multiplied by inverse meters squared. And now the meter cancels at the top here and the squared cancels here. And so we get kilograms per meter second squared, or we could write that as kilograms inverse meters inverse seconds. So yeah, let's write that right here again. Right over here, kilograms inverse meters inverse second squared. Okay, so that's pressure in fundamental units, or force per unit area. Finally, we go to energy, which the derived units is joules, which is kilograms meters squared inverse second squared. And the thing is, there's a lot of things that produce energy. Mass times speed squared. Think of kinetic energy. The kinetic energy is the mass times the speed squared. So we can plug that in and see that that does indeed make sense. Mass kilograms meters per second squared. Yeah, that gives us kilograms meters squared inverse second squared. But force times distance does as well. If you think to physics, that the work that you do on something is the force times the distance. And work is energy. So if we look at force times distance, we have that's Newton meters, which is going to be equal to kilograms meters times inverse seconds. That's a Newton times mass. Yeah, that is going to be also kilograms mass squared inverse second squared. Because we have two masses here, so it's kilograms mass squared inverse second squared. And finally, we have pressure times volume. It might not be immediately obvious, but pressure times a volume also has units of energy. Pressure times volume, a Pascal times a meter cubed. Well, that's just a Newton per meter squared by the definition of what pressure is, force per unit area. If we multiply that by meters cubed, we get Newton meters, but we just showed that Newton meters has units of energy as well. So all of these are different ways of measuring, of the different ways that units have energy. And that is the introduction to SI units, especially thinking about derived units. So I would practice some of these, especially the pressure and the energy. They'll come back later in the semester. There we go.